Let's talk briefly about the combined gas law now, which is something that you probably saw or learned to use in your previous chemistry experience before you got to Chem 111. The combined gas law is usually written like this: P1 V1 over T1 equals P2 V2 over T2. How would I know when I'm going to use this? Well, if I have two pressures in my problem, or two volumes in my problem, or two temperatures, then I'm going to need to use the combined gas law because something's obviously changing. If I don't have anything changing, if I just have one of each thing, I would use the ideal gas law, which is PV equals nRT. And what I want to do right now is to show you that these two are exactly the same thing, really. I mean, they come from the same place. It's just two versions of the same thing. We said on the ideal gas law page that PV over NT equals R. Well, that's going to be true for any set of conditions, right? So anytime we know the pressure, volume, and temperature, we know the number of moles. If we know the number of moles, pressure, and volume, we can figure out what the temperature ought to be. If we know the temperature, moles, and pressure, we can figure out the volume. Because every set of conditions that you can have an ideal gas under will always, these four things will always equal R. So what I want to do is say my first set of conditions, where pressure times volume divided by number of moles and divided by the temperature, that set of conditions is going to equal R. And if I change all of these things, they still have to calculate to make R. So let's say I have high pressure and volume, temperature. I could figure out the number of moles, right? And let's say we lower the pressure and the volume. Well, the temperature is going to have to compensate for that, so that the system still equals R. If both of these things equal R, then they equal each other, and so we end up with P1 V1 over N1 T1 equals P2 V2 over N2 T2. It turns out that if any of these things stay the same, stay constant from the beginning of the problem to the end, then we can just knock them out of there because they would cancel out mathematically. Let's say we have 2 moles of this gas. Well, if we have 2 moles at the beginning and 2 moles at the end, we would put a 2 in for N1, put a 2 in for N2, and then when we divide both sides by 2, we're doing the same thing. It doesn't matter. We could just cross the ends out because they're the same. This is true with any of these variables. If my two temperatures were the same, for instance, I could cross them both out because they're the same, and it doesn't affect the problem at all. Then I would end up with P1 V1 equals P2 V2, which is Boyle's law, or one form of it. So you can see that after I've crossed off my ends here, it looks just like the combined gas law that we put up at the top that I'm fixing right now. Okay, that is the form of the combined gas law. It's a useful form because a lot of times we're taking a sample of gas. We're not changing how much gas we have. We're just taking the container and we're either expanding the container or we're heating it or we're doing something, and then we measure the pressure, or we change the pressure and we measure the volume that results. And so P1 V1 over T1 equals P2 V2 over T2 is a very useful thing for us. Let's look at our sample problem here. It says, what is the pressure of a sample of CO2 gas? Okay, do we care that it's CO2 gas? Actually, not, because the combined gas law is based on the ideal gas law, right? And under ideal conditions, it doesn't matter what gas we have, it will still obey that gas law. So that was just extra information we didn't really need. Now we're going to look at, we're going to say, what is the pressure of the sample if it occupies so many liters at such and such a temperature? So now I just have to decide who's ones and who's twos here. I don't really care whether you label this pressure that we're looking for as P1 or P2. The main thing that matters is that each set of conditions stays together. So in other words, if I decide this, I'm going to name this P2 because it's the pressure in the end, and I want that to be 2. Well, that's fine. It doesn't matter as long as we take the volume that it's at that pressure and make sure that that's V2, and then T2 had better be that same set of conditions. And you have to be careful about this because problems can be written in different ways that label, that make you kind of think, oh, gee, it's not always the first temperature that's T1 and the second temperature listed that's T2. Sometimes they're flipped. We can say from 10 degrees to 20 degrees, or we can say to 20 degrees from 10 degrees, and it would be the same thing. So in other words, the upshot of all that is just be careful when you're labeling your P1s, P2s, and V1s, V2s that you line them up correctly so that the pressure and volume and temperature at one set of conditions all have the same subscript. Okay, on to our problem here. We are going to solve for P2, right? That's the unknown here. So we have P1 V1 over T1 equals P2 V2 over T2. If I'm solving for P2, I really kind of want to get rid of V2. So I'm going to take that down to the bottom of the other side by dividing both sides by V2, and then it cancels out. I did this, and then it canceled, right? So I'm going to multiply by T2 on both sides. My T2 cancels on that side, and then I have P2 equals T2 P1 V1 over V2 T1. And all I've got to do is pop those numbers in. My P2 will equal 852 torr times 2.91 liters times 248 K over 300 K, and I'm not sure if I'm writing these in the same order, but it doesn't really matter, 4.92 liters. Now, my K's cancel, my liters cancel, I have torrs left. It just says what is the pressure. It doesn't say what is the pressure in atmospheres, so I can solve it for any pressure units I want to. Since it started in torrs, the easiest thing to do is just to leave it in torrs. I did, however, convert Kelvin. You can see that we have a 248 to a 300. That's a change of what, about 1/6, right, of the energy that the molecules have. If I had changed from 27 and negative 25, if I'd put those numbers in, I would have gotten something close to -1 as my ratio between them, and we don't want a negative pressure in the end. We're very much messed up if we do that. The pressure turns out to be off, and we certainly can't have a negative pressure. You always, always, always have to use Kelvin. And again, my sig figs, I started with 2 sig figs for my temperature 2 and for my temperature 1, but by the time they got into my problem, they had 3 sig figs, so I get to have 3 sig figs in my answer. Because when we're changing from Celsius to Kelvin, we are adding, and of course, when you add 273 and 27, get 300. Remember, the addition subtraction rule is that you just cut it off at the place value. So yes, we get to keep all 3 sig figs there.